How to manage tolerance stack-up in engineering design. Imagine building a machine where each part has tiny size differences. When assembled, these small variations can add up and cause big problems. That's what tolerance stack-up is all about. It's the cumulative effect of individual part tolerances in an assembly. If not managed well, it can lead to misalignment, excessive gaps, or even parts not fitting together at all. So, how do engineers keep this from happening? Let's walk through some practical steps. First, it's important to understand what tolerances are. Tolerance is the allowable variation from a specified size on a part. For example, if a shaft is supposed to be 20 millimeters in diameter, a tolerance might be plus or minus 0.05 millimeters. This means the actual diameter can be anywhere between 19.95 and 20.05 millimeters. When multiple parts with their own tolerances come together, their variations add up. That's the stack-up. Knowing when to analyze this is key. You should check for tolerance stack-up when parts need to fit tightly, like in press fits or slip fits. It's also important when aligning features across several parts, such as holes or optical paths. If gaps or precise motion are involved, managing tolerances becomes critical. There are different ways to analyze how tolerances add up. The worst-case method assumes every tolerance is at its maximum limit at the same time. This gives a very conservative estimate, ensuring the assembly will always fit but often leading to tighter, more expensive tolerances. On the other hand, the statistical method, called root sum square, assumes tolerances vary normally and independently. It combines the variations mathematically, often allowing looser tolerances and reducing costs. For complex assemblies, Monte Carlo simulations can be used. These run many random samples to predict how the tolerances might behave in real life. Next, you need to identify the critical path in your assembly. This means pinpointing the sequence of dimensions that most affect the final fit or function. By focusing on this path, you can analyze how each tolerance contributes to the overall variation. Using geometric dimensioning and tolerancing symbols helps specify tolerances clearly and functionally. This reduces unnecessary tight tolerances and makes manufacturing easier. Balancing the tightness of tolerances is also important. Tighten tolerances only where they are truly needed for function or fit. Use the results from your stack-up analysis to adjust tolerances on individual features. This way, you avoid making parts more precise than necessary, saving time and money. After designing, it's smart to verify your assumptions. Use prototypes and inspection data to see if the parts and assemblies match your predictions. If they don't, you can tweak the design or tolerances accordingly. This feedback loop helps keep everything on track. In real-world applications, managing tolerance stack-up prevents issues like misalignment in car assemblies or gear trains. For example, in a gear train, controlling how tolerances stack ensures gears mesh smoothly and rotate without binding. In a multi-hole plate, it guarantees holes stay within acceptable limits, maintaining strength and function. By carefully analyzing and controlling how tolerances add up, engineers can create reliable, well-fitting assemblies. This approach reduces waste, cuts costs, and ensures the final product works as intended. Managing tolerance stack-up is a vital part of good mechanical design and manufacturing success.